All right. Well, welcome everyone live with We Need Our Space Live. Let me get my phone out of the way. Okay. Very special show planned here today. We're going to be going out to the outer reaches of our universe. Before I begin, I need to make sure I got some stuff running right. Bear with me for a second here. Today we are going to be broadcasting live for the first time on not just YouTube, but also Facebook Live and Twitch. So, right. Everything seems to be running fine. All right, good deal. Hopefully the music isn't too loud. Right, let me just shrink myself down. Bye. That's good. And let's begin. We need our space live. Okay. Well, to begin with, we're going to be starting off at Earth again, but this time we are not going to be starting off in Baton Rouge. I have picked a random place on the Earth to begin. A nice little mountain range here. I have no idea where this is at. I just kind of picked a random spot on the globe and zoomed in. And we can see that we have some little areas in it. That would be a nice little place to live, huh? Let me see, make sure. All right, good. Let's begin by lifting off the planet Earth. We have a lot to cover today. We're going to be leaving these nice mountains here. And I completely forgot what continent we're even on. I think we're somewhere above Italy, actually. So let's leave Earth. Leave that nice little vacation spot, probably. There we go. Yep, right above Italy there. Okay. And there we are. Leaving planet Earth. We have a lot of ground to cover today. So I'm going to begin like I always do, and I'm going to adjust our orbits here so that we are symmetrical, because I like symmetry. Alright, now the lines you're seeing here, again, those are the orbit lines. This blue line represents the orbit that the Earth takes around the Sun, and these other lines behind us, those represent the other orbits of the other planets. We have Venus, Mercury, Mars, Jupiter, Uranus, you know, all the planets. So we're not going to recap the last 2 weeks that we went to. Let's see, the first time that we went out here, let me speed up time. We went off to the inner planets, as well as taking a look at the Oort sphere, some crazy things like the radiosphere. And then last week we went to the outer planets, as well as looking at some of the... What did we do? Yeah, we looked at the Milky Way galaxy and a little bit beyond that. Today we're going to be going off to the first imaged black hole, the Orion Nebula, and some other planets in our solar system that you may have never heard of before. So we have left planet Earth now, and the first thing I'm going to do is I'm going to pull up some constellation lines, because we're going to look at why exactly we still use constellations. So when I use these constellations, I have these boxes on here as well. All the constellations in the sky occupy an area of the sky that looks a little bit like a map, kind of like a map of the US. Again, I have to make these boxes just like that. All right. So if this is the daytime side and we are on the nighttime sky, looking up, we have a very wide angle view of the sky. The constellations do look very large here on the screen. But again, remember, if you're a little tiny dot right there looking up at the sky, you would have many constellations at your disposal. So if we are in spring and we are looking up at the nighttime sky, there are some very easy constellations to find. I'm going to go over why we still use those constellations. So the easiest constellation to find in spring is going to be Leo, right over here. And let me just make sure that my cursor is being viewed. Yes, you can view my cursor. So we can find Leo. Easy to find Leo. There is this backwards question mark or sickle shape in the sky. And if you are having a hard time finding it from your backyard, here's the way it looks from my backyard. So this is an image I took across the street, and you can see there's plenty of light pollution. There's this football field, these street lights here. So if you look up, you'll find that backwards question mark. If you're having a hard time finding it, here's the outline of Leo. Again, there it is. I've kind of outlined those stars to kind of help you out a little bit. So easy to find Leo, and quite a large constellation as well. So again, if you're having a hard time finding Leo, all you have to do is use the Big Dipper. So we're going to rotate up just a little bit here. Now the Big Dipper, most people typically learn about the Big Dipper first. Excuse me. To find it, you're going to need to find this handle. You'll find the handle of the Big Dipper. These 3 stars form the handle of the Big Dipper. And then you will find the ladle, or the cup of the Big Dipper, these 4 stars. Now we can use the Big Dipper to find other stars. We can do some star hopping with the Big Dipper. To do that, what we're going to do is we're going to use these outer 2 stars in the cup of the Big Dipper. We're going to point our way down. Now, whenever you look at it from your point of view outside, this will look more like a straight line. So again, these 2 stars on the outer rim of the cup, point our way down until you find the brightest star below that cup, which will be Regulus. Regulus is the heart of Leo, the lion. I'll pull it up just a bit here. Now you will notice that Regulus resides along this path of the ecliptic. So again, here we are in our ecliptic. You'll see Regulus, that bright star there, lies along that line of the ecliptic. Now the ecliptic is an imaginary line that represents the apparent paths of the planets. So all of our zodiac constellations lie along that path of the ecliptic. Regulus is often eclipsed by the passing planets. Now what's interesting about Regulus is that today we're going to visit some of these stars up close. So there's Regulus. It means the little king, or the heart of the lion. Let's take a look at Regulus up close and personal. All right, this will be easy to find. All I have to do is type in Regulus, and we will find our way there. So, there is Regulus. Let's actually go up to Regulus, up close, to see what it looks like. Take away that little pointer there. Now Regulus resides 70 light years away from us. So it's going to take a little while to get there, so what I'm going to do is I'm going to speed things up just a tad, just to get there a little faster. So here we are at Regulus. Doesn't look that impressive right now, because when you look at Regulus, you're looking at several stars. You're looking at this bright star over here, and you're looking at this bright star over here. That star is actually a binary star, and that star is actually a binary star. What does that mean? Well, if we look at it this way, we can see that Regulus A has a companion star, which makes it a binary star system. And then there's another star, Leonis C, which has its own companion. So these 4 stars are sort of gravitationally attracted to each other. And whenever we look at Regulus, we're actually looking at several stars out there. But let's take a look a little closer at Regulus, the main star here. Let's go a little bit faster. There we go. Here we are at Regulus. We're a little close here. Let's back up just a little bit here. I'm going to speed up time a bit so that we can see these solar winds here. There we go. That looks nice. A little too fast. All right, moving it around here. There we go. You can see that nice shine of Regulus A. Well, here we can see that Regulus is a bluish white star. Now, this means it is very hot. Blue white stars are some of the hottest stars in the universe. It might sound a little counterintuitive because whenever we think of blue, we think of cold, and we think of red, we think of hot. When it comes to stars, it's a little bit different. So in your head, imagine a candle flame, all right? The very tip of the candle flame is going to be reddish orange. But when you look down at the wick of the candle flame, it's going to be blue. So blue and blue-white stars are the hottest stars. Red stars, red and orange stars are relatively cooler stars than that. You can see here Regulus A is a bluish white star. Well, Susan's seen that there are many different types of stars out there. Let's go back into here. Now we just found Regulus. Let's go back up to the Little Dipper because we're going to find another star to look at. So here we are at the Big Dipper again, right up the top. You'll find the handle of the Big Dipper. So we're going to use this handle of the Big Dipper to arc our way down to Arcturus. Now this might be a bit more difficult to find than Regulus, so here is a picture of Arcturus and Boötes from my backyard. So again, here is the Big Dipper. Find the Big Dipper, arc your way down to the brightest star you see. That will be Arcturus. Arcturus is the brightest star in the constellation Boötes. Boötes the herdsman. Now, Boötes might sound like a strange name. Well, the name could be translated from the word noisy, which could mean that the herdsman is shouting at the bears in his keep, the Ursa Major and Ursa Minor, the greater and lesser bears. In fact, the Big Dipper is not really a constellation. It is called an asterism. Asterism is part of a major constellation or several constellations. So the Big Dipper is part of Ursa Major, which means the Great Bear. The Little Dipper, Ursa Minor, means the lesser bear, the small bear. And the herdsman appears to be shouting at these two bears because as the sun and the stars appear to rise and set from east to west, we will see the stars and the constellations sort of almost revolving and rotating, moving around the North Star. So it does appear that the herdsman is chasing those two bears around the pole star or the North Star. So again, here we are. Find the Big Dipper, find the handle of the Big Dipper, arc your way down until you find that bright star there. That is Arcturus, brightest star in Boötes, and we can visit Arcturus up close. So let's leave Regulus and let's go visit Arcturus. Go. And there he is in Boötes. Let's head off to it. Now, Arcturus is 36 light years away. It'll take some time to get there. And here we are at Arcturus. Now, we could look at it like we did before, kind of pull away from it and see those nice little solar winds spreading out into space, but let's take a close look at Arcturus. I'm going to change my camera setting so we can look at Arcturus like this. The surface of Arcturus. When we see this, it looks a little strange. The surface of a star. Almost like a countertop. I've changed my camera settings to not blind us here. But we can see this roiling and boiling surface. Scientists think that one day this star, Arcturus, will collapse into a white dwarf star since Arcturus has finished fusing the hydrogen in its core. So this surface might look a little crazy, but let me show you a video, an actual video of the surface of our sun. So this is courtesy of the National Science Foundation's Solar Telescope in Hawaii. What you're seeing is turbulent plasma arranged in a pattern of cell-like structures. These cells are an indication of violent motions that transport the hot solar plasma from the interior of the sun to the surface. This is known as convection. Well, whenever it gets to the surface, it cools off, it sinks back below, and then it repeats. You can see the same activity on Arcturus, just like you can see the same activity on all the stars. Now, it may appear black here, but that's because we've had to dial down the brightness, so it may appear dark, but is actually quite bright. Get out of that there. Where are we at? Oh yes, the surface of Arcturus, some 36 light years away. Let's back away from that. Change my settings back to where I like it. There we go. Okay. Well, we just arced our way to Arcturus, and now we're going to continue, and we're going to speed our way to Spica. So we had this hand on the Big Dipper, arced our way down to Arcturus, and then we're going to continue by going from Arcturus, and we're going to speed our way, or spike our way down to Spica in the constellation Virgo. And we're going to be coming back to Virgo in a little while, because that is where some interesting stuff is happening. So from Arcturus, go down until you find that bright star, Spica. Yes, we can visit Spica up close. So we just saw Regulus, bluish-white star. We just saw Arcturus, reddish-orange star. And now we're going to go visit Spica up close. So from Arcturus over to Spica. And there it is in the sky. Here's a little pointer of where it is at. There's the constellation lines there. We are very far away. We have left our solar system, and now we need to go back and visit Spica, which is considerably further up. It is around 262 light years from Earth. Before we begin, I spilled my coffee all over the place. I'm trying to be careful here. So here we are approaching Spica, and what do we see here? A very different scenario indeed. We are seeing that Spica is actually two stars. Two stars, again, orbiting around each other in space. We can find Spica in the constellation Virgo the Maiden. And we can see why it is so bright. It is two stars. Let's take a look at that from this perspective here. Cooperate. That's right. Well, these two stars are gravitationally bound to each other. So we'll find that many stars in our nighttime sky are going to be double stars and triple stars. Some even more than that. But now let's go back to, in fact, let me kind of go home here. Let's go back to planet Earth. As we go back to planet Earth, we're going to go back into this. Because this is why we use constellations today. We use constellations so that astronomers and scientists can communicate with each other on what they have found and where they have found it. For example, if we move over here, we will find the constellation Orion the Hunter. Here comes Orion the Hunter. Now, when we look at Orion, we will see a few interesting things. If we look up close, we'll see some reddish areas over here. We see how these stars are also different colors, different sizes due to their location and their relative size. And we see this little smudge of light just below the belt of Orion. Well, that is called the Orion Nebula. We can actually visit Orion up close. That's what I'm going to do now. It's quite a lovely sight. So let's find the Orion Nebula from Earth. Point this little fella out here. We kind of go down here. Now we are kind of upside down, so let's rotate around. Sun's getting in the way. There's Orion, and if we look at the constellation lines here, we can see what we were just looking at in the other program. But take this down. So there's the Orion Nebula right there. And now let's go and visit that up close. Well, the Orion Nebula is going to be quite lovely. In fact, many of the nebulae in our universe are very, very pretty to look at. As we get closer, we're going to see the reddish and the pink and the blue areas of this nebula. And we can see some bright areas on the inside as well. So if I were to fly into the Orion Nebula, we're going to begin to see how the gas is enveloping this area. We can see this over here called the trapezium. So while I talk about the Orion Nebula, I'm going to play this for you here. So the Orion Nebula is an enormous cloud of gas and dust. It's 1,300 light years away from Earth. Now, whenever we get close to it, we see these beautiful clouds of the pinks and the reds and the blues. Now, that represents the different chemical compositions, the different chemicals in this area. The reddish pink areas, that represents the hydrogen gas. The bluish areas represent the oxygen. There are, of course, other chemical elements, but the hydrogen is the most abundant. Now, if you were to look at this area here with your own eyes, with your naked eye, you wouldn't quite see this. The view you're seeing now represents a long exposure photograph, a long exposure representation of the Orion Nebula. Sometimes even multiple exposures stacked together. Our eyes are basically meat cameras. They refresh every few seconds, actually. So we can't actually use our eyes for long exposure. It doesn't do that, basically. But out here, we can see it for what it really kind of looks like if we were able to see this through a long exposure lens. The long exposure for cameras gathers more light, and the way it works is the shutter opens up, light comes in and it hits the sensor. So the longer the shutter remains open, more light can hit the sensor. Here we are, we're within the core of the Orion Nebula, and this is called the trapezium. It is a collection of stars relatively tight together. It's what is known as an open star cluster. We'll see these little bow shock areas over here called proplyds, which is the birthplace of other stars. Well, here we are back in the other program here inside the Orion Nebula. Now we're going to go back to, actually, let's go back to planet Earth. Now, we were just at the Virgo Constellation. Now, within the Virgo Constellation, there is something called M87. As I promised before, there was the first ever imaged black hole. Very difficult photograph to capture. So we're actually going to travel to that black hole right now to take a look at it up close. It's actually named Poveghi. I'll get into why it's called that in a second. It's an interesting name. Again, Virgo is a spring constellation that you can find in the zodiac area of the sky. Now, it is within this constellation here. Let's go into the other program to take a look at this location of the black hole. Here we are. Constellation looks a little bit different sometimes. Constellations vary from place to place and how they want to arrange the sticks. I'll point out, there it is, M87 right there in the upper quadrant of Virgo. So let's visit that. Now we have left our star system behind. Now all these little dots you see here, those are not stars. Those are going to be actual galaxies. So traveling quite a long way away. 54 million light years away. And here we are at that black hole. Now I'm going to get into more detail. We're going to get closer to this, but right now this is what we're seeing as far as the black hole goes of M87, named Poveghi. So I'm going to get closer to it. And now we're going to begin to see this accretion disk around the black hole. I'm going to orbit up slightly here. Move in a bit closer. Alright, that's what I wanted to see. And what I'm also going to do is I'm going to speed up time much more so we can see the spin. Here we go. Checking out how this thing looks as it spins. Here we are surfing along the accretion disk of this black hole. That lens flare out of the way, not necessary. Get a little bit closer. And what I'm going to do is I'm going to change my camera settings. A tad closer so we can begin to see the shadow of the black hole. So here we are. Let's slow this down just a tad now that we're closer to it. All right. Well, here we are 54 million light years away from Earth. And we see this odd hump here. I'll get into why we're seeing that in a second. It's due to gravitational lensing. What happens is the objects that appear behind it are warped from how immense the gravity is. And that gravity distorts space and time. I just want to talk a little bit about the way this looks. So this is one camera setting here, and then I'm going to, and typically we wouldn't be able to see the stars behind it, but if I do this, we will begin to see how the stars look behind it as they travel. See these little stars behind it as they begin to warp. Okay. But anyways, let's concentrate on this right here. Exactly what we're seeing. Now, as I show you this, I want you to kind of pay attention to one interesting thing, how bright it is over here and how much it's not as bright as the area over there. So pay close attention to the difference in brightness between those two areas. So here's the actual image of the black hole that they took. This is just a computer simulation. The actual image of the black hole looks like this. I know it looks a little underwhelming, but keep in mind this is 54 million light years away. It's not super clear, but this was achieved because of 8 radio telescopes from around the world. Now, in order to see this black hole from so far away, they had to pick, first of all, they had to pick a black hole that had material around it, because it would be impossible to see a black hole. So they needed the material around it that is spiraling inwards to see this shadow of the black hole, as well as the heated up material that is circling around. So they would need a telescope the size of planet Earth to actually capture this image. Well, we couldn't build a telescope that large, so what they did was they have 8 radio telescopes located all around the Earth. And they synchronized these telescopes using an atomic clock to make everything perfectly in sync. And they were able to wait until the weather and all the locations were just right in order to capture this image. Well, what we're seeing here is the accretion disk of the black hole. That is the matter that is swirling around the black hole. This is swirling around at a fraction of the speed of light. So it gets very hot as it tries to spiral inwards. So it makes it extremely hot. Now let's go back over here to what we were just seeing. Now this bulge that you're seeing there, basically this is because the gravity of the black hole is so strong. Any light that grazes the outer limit of the black hole gets warped around the other side. So, for example, what we have here is a little record. Let's see if we can. There we go. This is just a plain vinyl record. Now, let's say, so you are over there. The camera is in front of me. So the light from behind this, where my face is at, as it goes over the surface of the record, it appears to be flat. That's because the record has no gravitational influence. It's a very small object. It appears flat. Well, the black hole itself is 6.5 billion times the mass of our sun. So 6.5 billion times that. It has incredible mass, has incredible influence. So imagine, I'm not going to use a picture of this because I want you to imagine this in your head. Let me just change the look at this for a second. As we look at this, kind of change our point of view since we're talking about something else. There we go. Look at that while I talk. So imagine in your head for a second a trampoline, and then you put a bowling ball on that trampoline. What's going to happen? The bowling ball is going to go towards the center, and it's going to kind of pull down. It's going to warp the fabric of that trampoline. So you have this bowling ball in the middle of the trampoline. Now imagine you put some marbles on the trampoline. What's going to happen to those marbles? Well, the marbles are going to go down towards the bowling ball because the bowling ball has warped the fabric of the trampoline. Well, again, now you have to think in 3D space. So not only would this black hole be shrinking, would be warping the fabric of space-time down, but also behind it, up to the sides as well. It's warping all of the space around it. So what we're seeing in this case of the record is as the light is going from behind it, it has to go over the black hole and warping over the black hole. The light from the side has to warp around it, and the light from underneath it has to warp around behind it. So if you were standing in front of this black hole, you would actually be looking at the back of your head. So think of it this way. So here's a black hole. So as light approaches it, it goes directly into the black hole. But as light comes from a different angle, it comes in and it warps into it. Then another bit of light comes in, warps into it. Now, if there is some light that is grazing along the path of this black hole, it comes around, warps around, and then comes around towards the front. So we are seeing light from the back of the black hole, from the bottom of the black hole, and from the sides being warped around it. That's why we're seeing this bulge here. It's called gravitational lensing. You're seeing it from the bottom, and we're seeing it from the top, and how it warps. If we move around, we'll see that little bulge move around with it as well. Now the size of this black hole is quite enormous. Now when I was a kid, I thought that a black hole would be just like a funnel in space, about the size of a spacecraft. But actually, the black hole that we're seeing here in M87 is so large you can fit our entire solar system in that shadow with room left over. Now the name of this black hole has been called, it's now called Pavehii. And that actually means the adorned, formless, dark creation, or the embellished dark source of unending creation. It's kind of a sweet band name. So if you're looking for a band name, there you go. I don't think Pavehii has been taken yet. Let's kind of go away from this black hole now. You've seen the way it actually looks in this computer simulation here. Now there is also a black hole at the center of our galaxy called Sagittarius A. We might look at that at a different time. So the black hole itself that you're seeing, that little black center there, that's about 23.6 billion miles across. Not counting the rings, just that black section there, the shadow of the black hole is 23.6 billion miles across. All right, so we did some deep sky flying here. Let's actually leave this and go back to planet Earth. Get over here. Now we did some deep sky flying. We went out to the Orion Nebula, black hole. Now I want to talk a little bit about some objects in our solar system that you might not have ever heard of before. These are going to be called the Dwarf Planets. Might sound familiar because Pluto was recently demoted from a planet to a dwarf planet. But there's more out there besides just Pluto. So for the time being, let's go visit Pluto up close, because we did have some interesting photos due to the New Horizons spacecraft. Head out past the orbits of Uranus and Neptune out into the orbit of Pluto. As we get closer, we will see the orbit lines of the moons, Charon, Hydra, Kerberos, Nix, and Styx. When we get out here, let me see if I can find the now famous heart of Pluto. There it is, right there. And just speed up time slightly. Go the other way, so we can see. There we go. Seeing the heart of Pluto. We can see this upper lobe there, and then this other lobe forming the heart of Pluto. Well, this region here looks very slick. Well, it appears to be made of nitrogen snow, as well as nitrogen, carbon monoxide, methane ice. And we can see that Pluto is another barren, lonely world. Get a little closer look here. It's this region called the Tombaugh Regio, named after Clyde Tombaugh, who discovered this. Now, as we approached Pluto, we saw some of those moons. Now, one thing I do want to point out is that the moon of Pluto, Charon, is spelled Charon, Charon, after the famous ferryman of the river Styx. So people think it's pronounced Karen, but actually Clyde Tombaugh had named this after his wife, Sharon. So it's spelled like Karen, but it is pronounced Sharon. It's a little bit of trivia there you can have for your friends. Again, the images of the surface of Pluto were courtesy of the New Horizons spacecraft. Well, there are other. Wow. You can see Earth here is going crazy. There we go. Had to decrease the speed. There we go. Now we're looking. I had to speed up time to take a good look at the black hole there. All right, now we're on better footing. All right, so here we are back at Earth. Now let's go and discover the other dwarf planets beyond Pluto. Now, we did talk about Ceres, another dwarf planet within the asteroid belt between Mars and Jupiter, but we covered that one, so now we're going to go and we're going to cover some other dwarf planets that you might not have heard of before. So we were just at Pluto. Let's go visit Pluto real quick in this particular program here. And there's Pluto. We just looked at that. There's that part of that heart shape there. But let's go out beyond Pluto. Let's go to a dwarf planet called Haumea. Haumea. A strange name, and a strange looking dwarf planet indeed. Looks almost like a pet rock, or an egg, or a potato. This is Haumea, and is named after the Polynesian god of childbirth and fertility. It also has two moons, named after the goddess's daughters. We have Namaka and Hayaka. Hopefully I'm not butchering those names there. But when we are out here, we are close to it, like this, we can see that it has a ring system to it. Now the oblong, odd shape is due to how fast this object is actually spinning. It spins quicker than anything in the solar system. taking just 4 hours to make one spin all the way around. Now, it was first discovered in 2004, just after Christmas, at the Palomar Observatory. It was first nicknamed Santa. I don't know why. But this is the 5th dwarf planet that was discovered. Now, out here, Haumea is around 43 astronomical units from the Sun. Now, I've covered what an astronomical unit is before. An astronomical unit is the distance between the Earth and the Sun. That is one astronomical unit. Haumea is 43 of those away. Now, beyond Haumea is something called Makemake, another Polynesian name. Let's go visit that. Makemake, another sort of strange-looking oblong, almost oblong shape. There we go. Well, Makemake, another one of those barren worlds covered in craters. Well, the discovery of Makemake, along with Eris, that we're going to be going to next, prompted the International Astronomical Union to reconsider the definition of what is a planet. Now, this is around 4.2 billion miles away from the Sun. It takes light from the Sun 6 hours and 20 minutes just to get to Makemake. It has a moon also. Really rolls off the tongue. S 2015-136472. Now, that is a provisional name. I'm sure they will come up with a better name in the future. And I did mention Eris. There is the last that we know of out here. It actually looks a bit more legit as far as a planet goes, or a dwarf planet in this case. This is Eris, not to be confused with Ceres. Now, Eris is only slightly smaller than Pluto, but it is a tad heavier. Now, it has one moon named Dysnomia, after the daughter of the Greek goddess Eris. However, when Eris and Dysnomia were first discovered, they were given the nicknames Xena and Gabrielle, after the characters from the TV show Xena Warrior Princess, for whatever reason. Now, way out here, we are 68 astronomical units away from the Sun, or 6,280 miles away from the Sun. But Eris appears to have these little shields of ice along its surface. Well, Eris is extremely reflective. It bounces back 96% of the light that hits it. This puts it on par with Enceladus, the moon Enceladus. Well, what constitutes a dwarf planet? And what is the difference between a planet and a dwarf planet? Why was Pluto kicked out of the planets? Well, the biggest difference is that a planet needs to be able to clear its path in its orbit. It has to clear out all the stuff in its neighborhood. The only thing passing its orbit has to be a temporary transit. Well, dwarf planets can't clear out their neighborhood. Planets also need to be spherical in shape and have relatively circular orbits. Well, the biggest difference between those two is how these dwarf planets are unable to clear their neighborhood. And that is why Pluto, Ceres, Eris, Haumea, Makemake are now considered dwarf planets. Now, we are approaching the 40-minute mark here. Maybe at 7 o'clock, I'm going to talk a little bit about Planet X, a proposed planet beyond Eris. Does it exist? Is it there? I'll get into that at 7 o'clock. Time being, we have wrapped up this episode of We Need Our Space. We've covered now the inner planets, the outer planets, the dwarf planets, and we have even covered some deep sky objects, such as the Orion Nebula, and we visited our own, we visited the M87 black hole. And maybe we'll see our own black hole at a later date. Maybe I'll do it today at 7 o'clock, if time allows. For the time being, let's go ahead and go back to planet Earth to wrap up this section of We Need Our Space. Now, I've showed you how to get home before. Today, let's just find some random spot on the planet to land controls are different from... Let's see here. Let's go over here to this mountain range I like so much. Right. And welcome back to planet Earth. Let's just touch down in this region here. There we go. And we will settle down. I don't know where we're at, but this looks like a fine place to land for the time being, and we will set up camp right here. As I get closer, that data will stream in from the internet, so we get a better look of where we are now stranded. Alright, and with that, thank you all for joining me today for We Need Space. I'll be doing this again at 7 o'clock. I'll put some more information in there for you. And with that, have a great rest of your day, and thank you for spending your lunchtime with me.